Welcome, dear students, to my channel Physical Chemistry My Way. Today, I am going to speak on Raman spectroscopy part 2. That is, in this presentation, we are going to discuss the pure rotational Raman spectra and the rotational vibrational Raman spectra with their properties. So, let us begin. Pure rotational Raman spectrum in case of diatomic molecule. First, we will see the selection rule for pure rotational transitions. So, only those rotational transitions are allowed for which del J is equal to 0 or del J is equal to plus minus 2. When del J is equal to 0, the scattered Raman radiation will be of the same frequency as that of the incident light, and that we called it as Rayleigh scattering. When del J is equal to plus 2, that will give us the Stokes line, and when del J is equal to minus 2, that will give the anti-Stokes lines in our Raman spectrum. Now, what is the Raman shift for a diatomic molecule? The energy of a rigid rotator is given by the equation Ej is equal to h square divided by 8 pi square I j into j plus 1. Or it can also be expressed as epsilon j is equal to Ej divided by h into c. So if you divide this expression of Ej by h into c, you will get the equation as h divided by 8 pi square I into c j into j plus 1 centimeter inverse. So this is the expression of energy of a rigid rotator, which can also be expressed as epsilon j is equal to b into j plus 1 centimeter inverse. So naturally B means it is given by h divided by 8ic pi square. As the selection rule for rotational transition is del J is equal to plus minus 2. That means for Stokes line, the del J will be equal to plus 2. Hence the molecule will be excited from J is equal to J level to the next rotational level with J is equal to J plus 2. Then in that case, the Raman shift will be given by del nu bar is equal to epsilon J plus 2 minus epsilon J centimeter inverse. Now as epsilon J is given by B into J plus 1 centimeter inverse. So here for this for this epsilon J plus 2, we will express it in the form of B into J plus 1. So here for J we will write as J plus 2, and for J plus 1 we will write as J plus 3 minus epsilon J is given by Bj into J plus 1. So if you solve this brackets, you will get the equation as 2B into 2J plus 3 centimeter inverse. And for anti-Stokes line, del J will be equal to minus 2. So in that case, the Raman shift is given by del nu bar is equal to reverse of this epsilon J minus epsilon J plus 2 centimeter inverse. So whatever value we get in equation 1, for anti-Stokes line you will get in the minus form, minus 2B 2J plus 3 centimeter inverse. So this is our equation number 2 for anti-Stokes line. That means if you compare these two equations, equation 1 and equation 2, the Raman shift, that is del nu bar, will be given as plus minus 2, 2b, 2j plus 3 centimeter inverse, where this rotational quantum number j is having the value 0, 1, 2, 3, etc. Now the wave number nu bar s of the corresponding spectral line is given by, for Stokes line, nu bar s is equal to nu bar I minus del nu bar. Okay, so if you substitute the value of del nu bar, that is the value of Raman shift, that is 2b into 2j plus 3. For Stokes line, the wave number nu bar s will be given by nu bar I minus 2b 2j plus 3 centimeter inverse. For anti-Stokes line, nu bar s is equal to nu bar I plus del nu bar. So here also for anti-Stokes line, you have to substitute the value of Raman shift from equation 2. So you will get this particular equation, that is the wave number nu bar s for anti-Stokes lines. Now the position of Stokes and anti-Stokes lines in the pure rotational Raman spectrum, in case of a diatomic molecule, are shown in the following table. So the following table gives us the idea about the position of Stokes line and anti-Stokes line in the pure rotational Raman spectrum. For example, here we have the first line, the rotational quantum number J is equal to 0 for the first line. The Stokes line, you get nu bar S is equal to nu I bar minus 6b. So here you have to substitute the value of J as 0, okay, because the value of rotational quantum number J is 0. So substitute in this equation, put the value of J is equal to 0, you will get this particular equation. For anti-Stokes line, the equation is nu bar S is equal to nu I bar plus 2b into 2j plus 3. So substitute the value of J as 0. As for first line, J is equal to 0. So you will get the position of anti-Stokes line as nu bar S is equal to nu I bar plus 6b. Now for the second line, the rotational quantum number, the value is 1. So put the value of J as 1, you will get this particular equation. In case of anti-Stokes line, you will get nu bar S is equal to nu I bar plus 10b. For the third line, put the value of J as 2 in this particular equation. Put J is equal to 2. You will get the Stokes line nu bar S is equal to nu I bar minus 14b. For anti-Stokes line, nu bar S is equal to nu I bar plus 14b. Similarly, for the third and the fourth line, you will get the position of Stokes line as well as anti-Stokes line according to this following two equation. So it is clear from the above table that the first line, that is Stokes as well as anti-Stokes line, it is separated from the Rayleigh line by 6b centimeter inverse. So here you can see in both the cases of Stokes line and anti-Stokes line, the first line is separated from the Rayleigh line by 6b centimeter inverse, whereas in the rest of the cases, that is for J is equal to 1, 2, 3, 4, the Stokes and the anti-Stokes lines are equispaced and they are separated by 4b centimeter inverse. So if here you would take the difference, 10b minus 6b, that is 4b, 14b minus 10b, that is 4b. So here the subsequent lines are equispaced and they are separated by 4b centimeter inverse, whereas the first line, it is separated from Rayleigh line by 6b centimeter inverse. Here this following figure shows the rotational transitions and the corresponding Raman rotational spectrum. Okay, as you can see here, this is the Rayleigh line, and the first Stokes line and the first anti-Stokes line, they are separated by 6b centimeter inverse from the Rayleigh line. Whereas the next subsequent lines in case of Stokes line as well as anti-Stokes line, they are equispaced. You can see the equal distance between them and they are separated by 4b centimeter inverse. That means the first Stokes line as well as the first anti-Stokes line, they are separated from Rayleigh line by 6b centimeter inverse, whereas the subsequent lines are separated by 4b centimeter inverse. In this you can see these are the rotational energy level, that is beginning from 0, 1, 2, 3, 4 up to 8. So this figure shows the rotational transitions here and the corresponding Raman rotational spectrum as shown in the figure. Now let us discuss about the second case, that is the rotational vibrational Raman spectrum. It is possible to predict theoretically that vibrational and rotational transitions may occur simultaneously in a Raman transition. So in such a case, the selection rules for diatomic gaseous molecules will be del J is equal to 0 plus minus 2, and for vibrational Raman spectra, del V is equal to plus minus 1. However, at room temperature, as most of the molecules are in the lowest vibrational level, that is V is equal to 0. Therefore, the significant vibrational transition will begin from V is equal to 0 to V is equal to 1, and this is called as the fundamental vibrational transition. Restricting to this vibrational transition only, the following results are obtained for rotational vibrational Raman spectrum. That means for del J is equal to 0, the Raman shift del nu bar is equal to WE 1 minus 2xe, that is called as the Q branch. For del G is equal to plus 2, del nu bar is equal to WE into 1 minus 2xe plus B 4j plus 6, that is the S branch. For del G is equal to minus 2, del nu bar is equal to WE into bracket 1 minus 2xe minus b 4j dash plus 6. So this is called as the O branch. Expressing the values for Q, S and O branch by del nu bar Q, del nu bar S and del nu bar O respectively. And if the wave number of the exciting radiation be nu I bar, the wave numbers of the Stokes line will then be given by nu bar Q is equal to nu bar I minus del nu bar Q. Nu bar S is equal to nu I bar minus del nu bar S. And nu bar 0 is equal to nu I bar minus del nu 0 bar. So here we have considered the case for only del V is equal to plus 1, which represents Stokes lines. For anti-Stokes line, del V is equal to minus 1, and they are usually weak because initially very few molecules are in the excited vibrational state. So these are the values. If you express the values for Q, S and O branch in terms of del nu bar Q, del nu bar S and del nu bar 0. Now here this particular figure shows the rotational vibrational Raman spectrum. Okay, here you can see the three lines, that is the O branch for del G is equal to minus 2, the Q branch for del G is equal to 0 and S branch for del G is equal to plus 2. So here these are the rotational quantum number, that is the J is equal to 0, 1, 2, 3, 4 up till 6 here. These are the vibrational energy level indicated by V is equal to 0, V is equal to 1. So each vibrational energy level is again subdivided into equally spaced or nearly equally spaced rotational energy level. Okay, that means many rotational energy levels here which are grouped together form one vibrational energy level. This is the second vibrational energy level, del V is equal to 1, and these are the corresponding rotational energy level for V is equal to 1. So this particular diagram, that is the rotational vibrational Raman spectrum in the case of diatomic molecule, is shown as above. That shows the O branch, Q branch and S branch. Now the selection rule for a molecule to give rotational vibrational Raman spectrum is that the polarization of the molecule must change as the molecule vibrates. Now in case of both types of diatomic molecule, that is homonuclear molecule as well as heteronuclear molecule, as the molecule vibrates, the control of the nuclei over the electrons changes, and so there is a change in the polarizability. That is why both the types of diatomic molecules, that is the homonuclear as well as heteronuclear diatomic molecules, give rotational vibrational spectra. That means they are vibrational Raman active. So this can be said to be the main advantage of Raman spectra over infrared spectra, because in case of infrared spectra, homonuclear diatomic molecules do not give pure vibrational or rotational spectra, okay, because they do not possess a permanent dipole moment. So this is a plus point of Raman spectra over the infrared or vibrational spectra. And thanks for watching my video. Please like, share and subscribe, and we'll come with another videos in the future. Thank you.